Okay, we're on section 3.1. Start with problem 14. So 14, 16, and 18 are problems where we need to find the critical number. The critical number is, well, there's two parts to the critical number. What are the critical numbers? And secondly, what good are they? Okay, so where they are is where the derivative equals 0 or the derivative is undefined. And the importance of the critical numbers is that the local extrema can occur at the critical numbers. They don't have to, but they will only occur at critical numbers. Now, for the most part, if you have vertical asymptote, that's where the derivative does not exist, but you won't have any local maximum, minimum. The only case where you'll have a critical number where the derivative does not exist and you will have a maximum is a cusp. We really don't do that much, so most of the time it's going to be where the derivative is equal to 0. That means that the horizontal tangent line is 0. So if we have a maximum, then we have a horizontal tangent line. If we have a minimum, we have a horizontal tangent line. We can't tell from this whether they are minimums or maximums. We just know that they are possible values of x. And there are cases where you have a critical number, you don't have a maximum or minimum. An example would be like x cubed, where here you would have a critical number, but you wouldn't have a minimum or maximum. So first we have to find the critical numbers, then we have to decide whether they are minimums or maximums by using the first derivative test, which is in the second section of this book. Okay, so our function, in this case g of x, is x squared times x squared minus 4. So there's two ways you could work this problem. You could use the product rule, or you could just multiply it out. We'll use the product rule so because we're going to use the product rule, I'm just going to call this h of x so that way. So it doesn't really matter what we call it. So if we have the product rule, you have the first function in the product and you have the second function in the product. And you take the derivatives of each part. Turns out the derivative is the same. The constant doesn't have any impact on this. And then we just cross multiply and add them together. So if we do this way, we'll get x squared times 2x, and then we'll add 2x times x squared minus 4. And we'll multiply out. So we'll get 2x cubed plus 2x cubed, 2x times x squared, and we'll get negative 8x. And then if you add the two terms that have the same, so we have 4x cubed minus 8x. Okay, so that's the derivative, h prime of x. So to find the critical numbers, we set this first derivative equal to 0. And then we solve for x. Okay, remember we don't cancel out the x, we factor out the x. So we can factor out 4x. 4x out of there leaves us with x squared, and 4x out of there leaves us with 2. So we have three solutions. We have x is equal to 0, and x equals plus the square root of 2, plus or minus the square root of 2. How did I get that? Because if I take this, I really, you can't factor that easily. So you set that equal to 0, you get x squared is equal to 2, take the square root, plus or minus the square root of 2. So we have critical numbers. And the critical numbers are x equals negative the square root of 2, x equals 0, x equals positive the square root of 2. And so at any of those three, we might have a local maximum or minimum. Just checking my solution here. want to get too overconfident of my math ability. Okay, so that's correct. Okay, we're on to number 16. So we have a quotient in this case. So let's change that to h of x. So f of x is the numerator, and g of x is the denominator. So we use the quotient rule. So before we use the quotient rule, we have to take the derivatives of each part. So that's what you get. So we know that h prime of x is 4x times 2x minus 4 times x squared plus 1. F of x times g prime of x minus g of x times f prime of x. Actually, that's the wrong way around, isn't it? Okay, let's try it again. So we take the derivative. So it's 4 times x squared plus 1 minus 4x times 2x, all divided by x squared plus 1 squared. So we need to simplify the numerator. So multiply everything out. 4 times x squared is 4x squared. 4 times 1 is 4. Minus 8 times 8x squared. All divided by x squared plus 1 squared. So we'll get 4 minus 4x squared, all divided by x squared plus 1 squared. Negative 8 plus 4 is negative 4. So we set this equal to 0. So the question is, when h prime of x equals 0, what values of x does that occur at? So we have 4 minus 4x squared over x squared plus 1 squared. So anytime you have a rational function and you want it to equal 0, you don't have to worry about the denominator. The only way that the rational function can go to 0 is when the numerator is 0. So we just set that, the numerator equal to 0. So if we factor out a 4, a negative 4, you'll get x squared minus 1 is 0. And if you factor x squared minus 1, you'll get x plus 1 times x minus 1. And so the numerator goes to 0 when x equals 1 and when x equals negative 1. So those are my critical numbers. And actually I'm going to plot this, so just bear with me. You can always plot these things to see if you got them right or not. So here we go. So the function we have is 4x divided by the quantity x squared plus 1. So that's what the function looks like. And at x equals negative 1, we have a critical number, and at x equals positive 1, we have a critical number. And you can see that we have a local maximum here and a local minimum there. Let's go back to the first problem, which was 14. And let's just look at that. Just to show you what that graph looks like. It's a fourth order equation because it has x squared times x squared, which is x to the fourth. So there is what it looks like. So we got the answers of negative the square root of 2, 0, positive the square root of 2. So those are the three critical numbers. And you can see we have 2 local minimums and 1 local maximum, so that makes sense too. So we'll probably plot these just to show that's what you do. Okay, next we have 18. So this is a trig function problem. So we have f of theta is equal to 2 secant theta plus tangent theta. And we're going between theta between 0 and 2 pi. So what this means is probably we have infinite number of solutions, infinite number of critical numbers, so we're going to limit it by limiting the domain of the problem. So f prime of theta. So we're taking the derivative with respect to theta. So we just do a normal differentiation. The derivative of the secant is the secant of theta times the tangent of theta. And the derivative of the tangent is secant squared of theta. That's just from the book in that table in chapter 2. So now we set that equal to 0. And then we solve for theta where this goes to 0. So it's not quite as simple. But you do see we have secant and secant in both of them. So probably the best thing to do is to factor out the secant. So we'll end up with secant theta is, and then what we have left is 2 tangent theta plus secant theta equals 0. Well, this has no solutions because the secant, this can't give you anything because secant is always greater than 1 or less than -1. So this never goes to 0. So since secant of theta doesn't equal 0 ever, we just kind of like, we ignore that one. It doesn't give us anything. So we have the second. So we have 2 tangent theta plus secant theta equals 0. So what values of theta between 0 and 2 pi? Where does that go to 0? So probably the best thing to do is to convert to sine and cosine. So we have 2 sine of theta divided by the cosine of theta plus secant, which is 1 over cosine of theta. And that equals 0. So if we multiply by the cosine of theta, we get 2 sine of theta cosine of theta plus 1 is equal to 0. And now what do we do? All we need to do is get this somehow in terms of just one variable, either sine or cosine, one trig function. And it turns out there is a trig identity, which I'm trying to find my trig identity stuff. Unfortunately, my book doesn't have them in the front of the book. So I'm looking for a book that does have it in front of it. Oh, there we go. A newer edition. So hopefully in the front of your book, you'll see on the trig section it says that 2 sine theta cosine theta is 2 sine of 2 theta. So this can be rewritten as 2 times the sine of theta plus 1 equals 0. So now what do we do? 2 sine of theta is equal to -1. And you take the inverse sine. But in reality, we can't just take the inverse sine because that would limit our domain. So, but we're going to do it anyway. I want to explain why I can do that. Okay, so you take the inverse sine of both sides. So the inverse sine of the sine is just the number. And then you get the inverse sine of -1. The angle whose sine is -1. And so the question is, between 0 and 2 pi, so here's 0, here's pi, what values of theta, so that's inverse sine, the angle whose sine equals -1. Well, we know that y is equal to the sine of theta, and we know that x is equal to the cosine of theta. So this is a unit circle. So y is equal to 1 at so when you take that, just that part, you get pi over 2, and you also get 2 theta is equal to 3 pi over 2. Is that true? That's not true. Angle of sine is -1. It's not a pi over 2. It's just 3 pi over 2. So you get 3 pi over 2. So theta divided by 2, you get 3 pi over 4. So I think that's right. So we have one critical number. You can always check it out by plugging it back in to let's say right here. So let's try that. So 2 times sine, I can make sure I'm in radians, which I wasn't. 2 times the sine of 3 times pi divided by 4 times the cosine of 3 times pi divided by 4. And I get -1, and you add 1 to that, and you get 0. So, looks like that might be the only time that happens. Just thinking if there's any other possibilities. I think so. So let's just check it out. So my answer is we have one critical number here at 3 pi over 4. So we're going to share. I'm going to go back to the original function that we had. So the original function we had was 2 secant, and we'll do secant of x because I don't like theta, plus the tangent of x. And we're going to go between 0 and 2 pi. So I'm going to put x min is 0, and x max is 6.4. That's about 2 pi. And we're going to just graph it and see what happens. So, so you can see we get one critical number right here, which is about 3.5. So let's see what. So what was my answer? Let's go back here. I said it was 3/4 pi. 3/4 pi. 3 divided by 4 times pi. 2.35. Apparently I've done that one wrong. Okay, let me go back. So, see that we all make mistakes. So the question is, what did I do wrong? So I'm just going to go back and look at it. Okay, so we have the original function, take the derivatives, factor out the secant. We get that, we change it to sine over cosine, 1 over cosine, multiplied by the cosine, we get that, use the trig identity, so we take the inverse sine of that. So it's the angle whose sine is -1, 2 times theta. So and actually it worked out. So why isn't that not working? Okay. let me just check the answer in the book, which you guys can't do, but I get to do. Well, looks like I'm pretty close to being what they are. I don't know exactly what the issue is, so I'm going to hold on. I'm going to pause for just a second. Okay, so I see what I did wrong. Didn't take too long. Okay, so here's my error. When I multiply by the cosine of theta, I get that. So we will erase all that stuff. So if I multiply by the cosine of theta, I'll get 2 sine of theta plus 1. And so I get that the sine of theta is equal to -1/2. So we subtract 1, divide by 2. So under what values of theta does the sine equal -1/2? Well, it's the value where x is -1/2, or y is equal to -1/2, based on this thing. So you get that angle, and you get that angle. And so that is going to be the angle in the third quadrant. Well, let's do this my way, which is using the reference angle. So the reference angle, you take the inverse sine of the absolute value of the number, -1/2. And if you do that, so you take the inverse sine of 1/2. So inverse sine of 1/2 is 0.5235. That's radians. So I'll say theta reference. Now, because the sine was negative, we know the answer is in quadrants 3 and 4, because that's the quadrants where the sine is negative, right here. So the y's value. Okay, so what we do is we take the reference angle. First, we're going to convert that to some fraction of pi. 5.253, you multiply by pi, you divide by pi. So we actually do follow this calculation. So we take that and we divide by pi, and we get 0.166 times pi, and that is pi over 6. If we got 0.33, it would be pi over 3, and if it was 0.25, we get pi over 4. So that's my reference angle. Now, in the third quadrant, the angle is just pi plus the reference angle. So you take pi plus pi over 6, that's 7 pi over 6. And in the fourth quadrant, theta is equal to 2 pi minus the reference angle. So that means that you get 2 pi minus pi over 6, and that's 12 pi over 6 minus 1 pi over 6, and that leaves 11 pi over 6. So these are the two answers which do match up with the graph in this problem. Okay, we're moving on. And let's see, where are we? Okay. Okay, so we're on problem 23, and it says locate the absolute extrema of the function on the closed interval. So we're going to find the critical numbers, and then we're going to do something with that. So what we can do is, we haven't learned the first derivative test, so basically what we have to do at this point is to just evaluate the function at the extreme, or the critical numbers, and evaluate them at the end of the intervals. So you'll notice that these do have an interval specified, so they don't go from negative infinity to positive infinity. So there's the function, and the interval in question is -1 to 2. So we're going to evaluate the function at these two values, plus we're going to find the critical numbers by taking the derivative. So the derivative of x cubed is 3x squared. We subtract the derivative here, you get 2x, the 2's cancel out, and you're left with 3x. Okay, so then we find the critical numbers by taking this, setting equal to 0 to find out where we have horizontal tangent lines. Also, notice that this derivative exists everywhere because it's just a polynomial, so there's no cusps involved. So we factor out the x so we don't lose that solution, and we also factor out the 3. So that means we have critical numbers at x equals 0 and x equals 1. Okay, now that we have that, we're going to evaluate the function at 4 values of x. We're going to do f of -1. We're going to do f of now these two are inside. So if one of these critical numbers was outside the interval, then we wouldn't evaluate that. We're just going to evaluate the critical numbers that are within the interval. So you check the ends of the interval, and then any critical numbers that are within the interval, and then you check the other side. So those are the 4 points. So let's just go ahead and stick those in and see what we get. So you're going to get -1. -1 cubed is -1 because it has an odd exponent. Here you get -1 squared, which is +1. So you get +1 times that, so it's going to be -1 minus 3/5, so that's going to be -5/2. Okay, f of 0 is 0. If we stick in 1, we're going to get 1 minus 3/2, which would be -1/2. And then if we stick 2 in there, so we'll get 2 cubed minus 3/2 times 2 squared. So that's 8 minus, so we're going to have 3 times 2 times 2 divided by 2. So that's the same as just 3 times 2. So we're going to have 8 minus 6, which is 2. So at that point, to find the absolute extrema, you look for the smallest number, most negative number, which is this one, -5/2, and you look for the most positive number, which is this one. So it turns out the ends of the interval are the most negative and most positive, even though there are local extrema between the left and right-hand side. So we're going to prove this by plotting this thing. So the original function was x cubed minus 3 divided by 2 times x squared. And let's just do x min. Our interval is from -2 to 2, so let's go from -2 to +3. And we'll graph it and see what it looks like. So there it is. So here is x equals -1. We get -5/2. So you can see that's the minimum. If I draw a horizontal line here, you can see there's no point that's below that. Here's the local extreme at x equals 0, which is 0. Here it is at x equals 1, which is negative 1/2. And then at positive 2, we got positive 2. So that you can see that this also, the right-hand part of the interval, is also the maximum. So even though we have local minimums and maximums, the maximum and minimum on the interval from negative 1 to 2 are the endpoints. So is that what we said? Yep, there we go. Everything matches up with what we did analytically. Okay, we're now at problem 28. So 28 is a rational function. Actually, it kind of looks like the one we did earlier. So we have 2x over x squared plus 1. So it is similar to what we did. If you look at problem number 16, you'll see that it's basically the same function except that it's multiplied by 2 instead of 4. And their interval is from negative 2 to 2. So we take the derivative, and we're going to use the quotient rule. So we're just going to call that h of x. So we're going to let f of x be the numerator, g of x be the denominator, take the derivatives of each part of the quotient, we get that. So h prime of x, which is the original function, we take the derivative of the first, or the numerator, times the denominator, minus the derivative of the denominator times the numerator, all divided by the denominator squared. And so we can clean up the top here. So we get 2x squared minus 4x squared, so that's negative 2x squared. Negative 4 plus positive 2, and then we get a plus 2. All over x squared plus 1, quantity squared. So, again, for a rational function, we just have to look at the numerator to find out where we have critical numbers, the numerator of the derivative. If we look at the numerator of the original function, where that goes to 0 are the x-intercepts. So we have an x-intercept at x equals 0, because that's the value of x, which would make that go to 0. But it turns out if we factor out a negative 2, we'll get x squared minus 1 is equal to 0. So our two solutions, well, let's factor that. So you get x minus 1, x plus 1. So our two critical numbers are at x equals negative 1 and x equals 1. We have an x-intercept at x equals 0. So those are our critical numbers. So are those critical numbers, or either of those critical numbers, inside of our interval? Yes, they are, because negative 1 and positive 1 are between these two. So just like before, we're going to evaluate the function. And remember, the function is 2x over x squared plus 1. So we want to do the function at the left part of the interval, the one critical number, the other critical number, and the right. So now we just plug this in. So we'll get negative 2 over 5. Negative 2 squared is 4. 4 plus 1 is 5. H of negative 1 will get, oh, that's not right. It's 4/5. 4/5. 2 times negative 2 is negative 4. Okay, this one will be negative, the numerator will be negative 2. The denominator is going to be positive 2. Negative 1 squared is positive 1. 1 plus 1 is 2. Okay, at x equals positive 1, we end up with 2 over 2. And So you see this is going to be symmetry. This is going to be 4/5. 2 times 2 is 4. 2 squared is 4 plus 1 is 5. Okay, so we look again at these and say, okay, well, so we can simplify this. -1, +1. So which is the most negative number? That. And which is the most positive number? That. So in this case, the end points of the interval are not the maximum or minimum, but points inside that. And yeah, and it just asks us to locate the absolute extreme. It doesn't actually ask us what they are, but these are the values. So again, we're going to go to the graphing program and prove that we did this correctly. If we didn't, we'll fix it. So we have 2x divided by the quantity x squared plus 1. And the interval was from -2 to +2. So we'll go from -3 to +3. So there you go. So here is, so f of -2 was -4/5. F of -1 was -1. F of 0 is 0. F of 1 is +1. F of +2 is +4/5. So you can see this is the absolute maximum, and this is the absolute minimum, which occur in this case the critical numbers. So we're in problem number 30. So this is another rational expression. In this case, because the denominator can go to 0, we do have a vertical asymptote. But the vertical asymptote occurs at t equals 2, so the interval does not include the vertical asymptote. Okay, so let's say f of t is the numerator and g of t is the denominator. So what we can do is take the derivatives, taking the derivative with respect to t. So now we use the quotient rule. So we take this times that, which would be t minus 2 times 1, and we subtract 1 times t, and we divide by t minus 2 quantity squared. And we'll go ahead and fix up the numerator. So the t's cancel out, so you just end up with -2 over t minus 2 squared. So what we've done in the past is we said, what values of t does the numerator go to 0 for the derivative? So that we have a horizontal tangent line. In this case, it never goes to 0. So this has no minimums or maximums or local minimums and maximums. So all we have to do in this case is we just have to evaluate the functions at the upper and lower limits of the interval. So at 3, we get 3 divided by 3 minus 2, which is 3. And we get 5 divided by 5 minus 2, which is 5/3. So our maximum is 3, and our minimum is 5/3. And just checking the answer here. I didn't check the last one, but yep. So that's all there is to it. So you don't necessarily have to have local minimums and maximums. And again, I'll plot the function while we're at it. Don't take very long. So we go from, so our function is x divided by x minus 2. And the interval is from 3 to 5, so let's go from 2 to 6, just so we can see the entire thing. We say graph it. So there we go. We have vertical asymptote at t x equals 2. So at x equals 3, you get 3. And is that what we got? Yep. And at 5, we get 5/3. So at 5, we get 5/3, which is there. So we just have the endpoints of the minimums and maximums. Okay, so our last problem in this section is number 33. And so we get the cosine of pi x, and the interval is from 0 to 1/6. Okay, so take the derivative, f prime of x. Okay, the chain rule, we've learned this, is if you have the cosine of some constant times x, then the result is that constant, which is pi, times the derivative of the cosine, which is the sine. The argument in this trig function remains the same, and you have a negative sign because the cosine derivative is negative the sine. So this constant becomes outside. It doesn't really come outside. Through the chain rule, it gets multiplied by pi. Again, you think of it, this would, f of u would be cosine of u of x would be pi x. So the derivative of pi x is just pi. And the derivative of the cosine is negative the sine of u, so you get negative the sine of pi x. Okay, so that's the answer. So the question is, and they set that equal to 0, and you say, okay, what values of pi does this go to 0? Well, the pi in the front drops out, so you just have to answer the question. What values of x does the sine of pi x equal 0? Well, obviously 0 is a solution. There are other solutions, which I think I'm going to show you how to do that. But I don't think there are any other solutions. If you put in 1/6, you get pi over 6. And we know going from pi of sine of 0 is 0, and the sine of pi over 6 is 1/2 from the unit circle. It doesn't go up or down. So in this case, again, it's just the ends of the interval that would be the case. But let's not worry about that. Let's answer the question. What values of x does this go to 0 for x between 0 and 2 pi? So let's answer the first part of the problem. So the answer is this goes to 0, adds 0, but that's also the endpoint, so we don't really have to do it twice. So all we'd have to do is evaluate the function, the original function, at the endpoints. So you have the cosine of pi times 0. The cosine of 0 is cosine of 0. Cosine of 0 is 1. And f of 1/6 would be the cosine of pi over 6. And the cosine of pi over 6 is the square root of 3 over 2. So the minimum would be this, and the maximum would be that. Because the square root of 3 is something like 1.732, so 1.732 divided by 2 is less than 1. So this would be your minimum, and this would be your maximum values, and the location would be at the endpoints. Okay, now back to the other one, because you're going to do this later, and so I want to demonstrate the procedure as much as I can. So the procedure I want you to use is using reference angles, because using the unit circle is only good if the answers are pi over 6, pi over 4, pi over 3, etc. And that doesn't always happen, and it's not going to happen in this case because you've got this pi multiplier by the beginning of it. So let's. So what we would do is we normally would take the inverse sine, but what we did we take. So the first thing you do is you do the inverse sine, and you use the absolute value of this number, which of course the absolute value of 0 is 0, so the inverse sine, the angle whose sine is 0 is 0. Are there other cases? Well, so I'm just thinking here. Inverse sine of, oh, that's right. So what you get also is you get pi x over here. Okay, so when you take the inverse sine of the sine pi x, you just get pi x. So one of the solutions is an angle, the angle of 0. Now the other one, there's two cases where the sine goes to 0, and that's also at pi. This is a weird special case, which is when you're on the x-axis. So the other answer is going to be pi. So then you solve the values of x where this is true, and so x will equal 1 is your second solution as far as the case where this derivative is 0. So we have two solutions. So we have a critical number when x equals 0, and we get a critical number when x equals 1. So let's just, and you would also get multiples, you know, at x equals 2, you get a critical number at x equals 3. So let's just prove that's true. So we're going to plot the cosine of pi x. Cosine pi x. I think that's how we do that. And we'll go from 0 to 2 pi. 2 pi, so we'll take 2 pi is 3.14, 6.28, 6.30. Put that there. And let's go from -2 to +2. So we have, so there we go. Oh, what happened? It's probably the pi, the way I did pi. So I think you do maybe, here's just some additional stuff. If we go to help, it gives you a listing of all the functions and what the format is. So it looks like you just put pi in there. Okay. And let's put, I don't know if that'll probably work, graph. There you go. Okay, so what I said was at x equals 0, you have a local maximum. At x equals 1, you get a local extrema. X equals 2, x equals 3, x equals 4, x equals 5, x equals 6. So, you know, this is the repeating situation. So between x equals 0 and 2 pi, you actually get 1, 2, 3, 4. Well, 1, 2, 3, 4, 5, 6, 7. I don't know if we conclude 2 pi, but 6 extrema. Anyway, the answer to the original question was, the minimum was, let me just check to make sure this is right, was at x equals 0 and x equals 1/6, which is the other side. So you don't have any extrema within that range. So what we were doing, what we were doing there was we were going from 0 to 1/6. The 1/6 is about right here. So you can see we get the maximums here, the minimums there. There's no up and down to give us any local minimums or maximums. Okay, this is problem 61. Forgot to do it initially, I'm not sure why. So it's a word problem. We have a lawn sprinkler is constructed in such a way that the theta dt is constant, where theta ranges from 45 to 135 degrees. The distance the water travels horizontally is this x is equal to v squared sine of 2 theta divided by 32, where v is the speed of the water, which should be a constant, and find dx dt and explain why this lawn sprinkler does not water evenly. What part of the lawn receives the most water? So if we take the derivative of both sides with respect to t, we'll get dx dt, and v is a constant, so we just keep that out there, divided by 32, and then we take the derivative of the sine of 2 theta, which is going to be 2 times the cosine of 2 theta. which we now know, hopefully, because if we messed up at the test, hopefully we know that now. Okay. And forgot d theta dt. So we have dx dt is equal to v squared over 32 times 2 cosine of 2 theta times d theta dt. So dx dt, because of the velocity of the water coming out, this is really a measure of how much water is being added to the lawn, because if this were 0, then it would just sit in one place and it would just water it. And because d theta dt is constant, the only thing that changes here is theta. So you can see that if we find the maximum, that's what they're asking us for, what part of the lawn receives the most. What we're doing is we're looking for the case where this dx dt is a maximum or is a minimum. In this case, we're asking for a maximum. So we actually can take the derivative again and I'm just thinking about this. So one way you could do it, we could just plot it. Or you can just say, these are all constants, so all this other stuff's constant. V squared over 32 times d theta dt times, no, actually it's 2 divided by 32 is 1 divided by 16. And then we have this cosine of 2 theta. So if we maximize this, then we maximize the, actually what we're trying to do is actually minimize this thing. So when d theta dx dt is the minimum, then you will get the most water in that particular part. So if you think about when is this 0, well, this derivative is 0 when this thing is 0. So the question is, when is the cosine of 2 theta equal to 0? Well, this is one of these cases where you would use the unit circle to look at it. So remember, y is equal to the y coordinate on the unit circle is equal to the sine of theta, and x is equal to the cosine of theta. So where the cosine of theta, so then we could say 2 theta is, when it's 2 theta equal to 0, when is, well, let's see, let's go back here. When is the cosine of 2 theta equal to 0? So what part on the unit circle is the cosine 0? Well, it's at pi over 2 and 3 pi over 2, which is 90 degrees and 270 degrees. But in this case, we don't go that high. So the max, so this is equal to 0 when this quantity, when 2 theta is equal to 90 degrees. Well, actually, it is true. 2 theta is the other solution. Is 2 theta is equals 270 degrees. So the actual values of theta, where that occur, you divide by 2, so you get 45 degrees, and theta equals 135 degrees. So it turns out that dx dt is a minimum. It's actually 0 when the angle is equal to 45 or 135 degrees. Let's just explain how that works. So you can see if I took the cosine of 2 times 90 degrees, that'd be the cosine of 180 degrees, which is actually 45, I forgot that. Okay, 45, so that's 90. 45 degrees. That's what's the cosine of 90 degrees? It's equal to 0. The cosine of 2 times 135 is the same as the cosine of 270, which is also 0. So this term goes to 0 when the angle is 45 and the angle is 135. It's at the end of the stroke. Basically, it comes to the end, and then so that means the maximum amount of water is given at the ends. So we could answer the question: what part of the lawn receives the most water? And the answer is when we are at the ends of the stroke. The least one that receives the least amount of water is going to be the center. Okay, let's pause for a second here. Okay, I just want to make sure I explained it. Did I explain it right or not? The other way to look at it is if I take the derivative of this thing, dx dt with respect to theta. So if I take d theta of v squared over 16 d theta dt times the cosine of 2 theta. Well, this stuff is all a constant, so that comes out front. So we take the derivative of that with respect to theta, and you would get 2 minus 2 sine of theta, 2 theta. Okay, so that's the derivative with respect to theta. So I'm trying to figure out what is the maximum, what is the angle where this thing is a maximum or minimum. So what I could, those are where the critical numbers. So what I could do is set that equal to 0. 0 is equal to v squared. So I'm setting the first derivative equal to 0. And it turns out all this stuff here is a constant. So ultimately, the minimums and maximums are going to occur at the sine of 2 theta when the sine of 2 theta equals 0. And again, we would say let x equal 2 theta. Well, let's call it w just to use a different variable. So I'm just substituting it in. W equals 2 theta. So we're going to say, you know, what values of w does that equal 0? Well, the y value is 0 at 0, and the y value is 0 at pi. So my two solutions to this are w equals 0. Also, we could say it's true at 2 pi as well. So it's the sine of w is 0 at 0, pi, and 2 pi. So those are my answers. Pi, 2 pi. Okay, now, so that's for w. So theta is w over 2. If we solve for theta. So my values of theta are going to be equal to 0, which is not one of our possibilities. And you get pi over 2, and you get pi. So pi over 2 is the case of 90 degrees, which is where we have a minimum. Now, as far as the other, right here, we said the maximums occurred at 45 and 135, and we did that by, how the heck did we do that one? Why is that not showing up? Yeah, they use this explanation in the book. I was trying to use another explanation to minimize that or to maximize it, and I thought I would get the same answers, at least, you know, that I would get 45 and 90. So I'm not sure why that is the case. Anyway, just take my first explanation.